single electron would be somewhere around 9.11 times 10 to the negative 28. Now these numbers are extremely small. When you see the exponential number goes to negative 20 something, that's a very small number. And keep in mind, these numbers are not measured in the laboratory. Rather, they are based on calculation. We don't really have a device to measure a mass that small. Okay, so when you talk about the mass and particle masses there, since they are so small, sometimes it's hard to comprehend how do we have such a small mass there. Then we use what we call an atomic mass unit. We have select one particular atom, for example. We use that as a standard. Okay, everything is compared to that standard. So in this case, the atomic mass unit, well, one atomic mass unit, well, we select the standard that we use is carbon. So we say carbon as an equivalent of 12 atomic mass units. And comparing an electron, mass of electron to carbon, well, electron is only about 0.000549 atomic mass unit. Okay, this is a number that's somewhat easier to comprehend compared to that number. Okay. How does the mass of the proton and neutron compare to electron there? You can see it's 1.673 times 10 to the negative 24. So that's a 10,000-fold difference there. Okay. You're talking about 10 to the 4th power difference there. Now comparing that, if you take one proton, compare the mass of the proton to an atom of carbon, well, carbon is 12 atomic mass unit, and proton is about 1.0073. So when we talk about the particle masses, there are two different units that we use. One is the absolute mass. We are using grams, and sometimes kilograms, to describe the mass there. The other is what we call the atomic mass unit. Okay. There is a relationship between the two quantities there, and well, you can basically this would equal to this. This is our conversion factor. Okay, so we can figure out the relationship between the atomic mass unit and the grams, but we are using these different units in measuring the when we're measuring the mass of the particles. There, we're using those two different units, in, depending on how what we're talking about. So we're going to get into the details about when are we going to use the atomic mass unit, when we're going to use the gram, and when we try to figure out the quantity of the protons and neutrons and electrons that we have, or even the atoms that we have there. The neutrons are about the same size, and if you look at the numbers there, they're pretty close to one another. Okay, so and 1.675 versus 1.673, and in terms of the relative mass there, 1.0087 atomic mass unit. Okay, so in this case, if you equate these two quantities together and say one atomic mass unit in terms of gram is roughly about 1.66 times 10 to the negative 24 gram. So you can see these are extremely small particles. We can't really see them. Okay, and electrons and protons in chapter 7, when we get into the quantum mechanics theory there, we will talk about the behavior of those extremely small particles there. And simply by shining a light, a beam of light on those little particles will change their behavior. So they behave quite differently from what we observe or what we experience in the macroscopic world. So these are the numbers that we have, at least up to this day, and we have this understanding. These are the relative masses or the absolute masses for the protons and neutrons and electrons. So the atom's mass there, if you look at the mass of the proton and the mass of the electron and neutron there, and if we say since the electron mass is about 2,000 times lighter than the proton and neutron, and atoms are made up of protons, neutrons, and electrons there. So when we try to estimate the mass of the atom, we can pretty much ignore the mass of the electron because they are so much smaller compared to the other two particles there. So when we try to estimate the mass of the atom there, we simply add the number of protons and electrons, protons and neutrons together, and then the mass of the electron is negligible. Now remember, we say 99.97% of the mass of an atom is in the nucleus. What about the other 0.03%? Well, 0.03%, give you a little perspective. If a person weighs 150 pounds, 0.03% of the body weight is about less than 1 ounce. So we should be able to reflect that mass there. So when we estimate the atom's mass there, we simply focus on the larger, heavier particle mass, neutrons and protons there. Okay, so the mass of the electron is negligible compared to the neutrons and protons there. Okay, so the properties of the particle there, as we mentioned at the beginning there, and there are the first two subatomic particles that were discovered first are electrons and protons, simply because protons bear a positive charge. So if you have a particle bearing a positive or negative charge, if you subtract that particle going through an electric field, now when you have a charged particle going through electric field, they are not going to go in a straight path. So they're going to bend, and the path through the electric field is not going to be a straight line there. So we discovered the protons and the electrons first, and indicating there's an electrical charge on the proton and electron there. But proton positive, electron negative. They bear the same amount of charge. Coulomb is the unit for the electrical charge there. So 1.602 times 10 to the negative 19 power, and proton positive, electron negative. Now, at that time when we first discovered, well, there were actually small particles within the atom there, and so maybe those are the two subatomic particles. Those are the only two subatomic particles there. However, people find out later on, the mass did not add up. So there has to be another particle in there, and this is how neutron. Neutron has no charge. And later on, neutron was discovered through other methods there. Okay? So the particle properties there, in terms of their size, in terms of their mass, in terms of electrical charge, and these are the things that we need to remember. Now, when we look at a particular atom there, we need you to be able to determine how many protons are there, how many electrons are in there, how many neutrons are in there, based on what we call the atomic number of those elements. So these are the basic things that we need to lay out first before we get to this part. Now, how do you represent a particular atom? Now, using a symbol X to represent any elements there, we have what we call an A number and Z number. What is an A? What is a Z there? On the left side of the atomic symbol there, so X is for any element there. Hydrogen H, carbon C, nitrogen N, so on and so forth. Okay, A is the number. A number is what we call the mass number. Okay, it's the number of protons plus the number of neutrons. Now, on the previous slides there, when we were estimating the mass of the atom, the mass of the atom would be the mass of the proton plus the mass of the neutron. So if you figure out the total number of protons and total number of neutrons together, if you're using the relative mass, atomic mass unit there, you add them together, A will give you the mass of the atom. Z is what we call the number, the atomic number, or the number of protons there. Okay, so the relationship between A and Z though is that the difference between A and Z will give you the number of neutrons. How about the number of electrons there? Well, we say an atom is charge neutral, meaning you have equal number